Hello. In previous units, we've learned about what a power series is, we've learned about geometric series, we've learned how to create a Taylor series or a Maclaurin series for a particular function. We're now faced with the question, what good is it? When will such a series converge? When will a Taylor series converge to the function that was used to create it? And if we use a Taylor polynomial, how accurate will our approximation be? Let's review a few tests for convergence. If we have a geometric series, we know exactly when our geometric series converges. And our geometric series, which takes the form constant times r to the nth power, as n goes from 0 to infinity, we know this will converge first term over 1 minus r when, and only when, our common ratio is less than 1. We've got geometric series taken care of. What about some tests for some other types of series? Well, the first test, and these tests that we're going to be discussing from now on apply to what we call positive termed series, where we have all addition in our series, no negatives. So the nth term test is really a test for divergence. In order for our series to have a chance to converge, the nth term of the series must go to 0. And so we say if the nth term doesn't go to 0, our series will definitely diverge. An example of this could be the series of n over n plus 1. As we look at the nth term of this series, we see that the limit of that term is 1, not 0. And therefore, our series diverges. I hope as you explore convergence and divergence, you will always check to see that the nth term at least goes to 0 for you to have a chance for your series to converge. All right, now that we know when a series will diverge, what about when will it converge? So we have something known as the integral test. And we say with the integral test that if an improper integral will behave the same way as our infinite series. And so if one converges, so will the other. If one diverges, so will the other. So let's look at a classic example of this. If we compare this integral 1 over x dx on the interval 1 to infinity, this is an improper integral, and you know that this integral diverges. We're going to compare this to the infinite series 1 over n. This is known as the harmonic series. It's a very well-known series. Now, even though the nth term of this series goes to 0, we can show that this series diverges. And a quick little picture will illustrate that. If we look at our function 1 over x, and we look at the left rectangles, starting at 1 of unit width, we see that the heights of those rectangles are in fact the terms of our series. And since our integral diverged, and these rectangles give us an area bigger than that of our integral, we know that our harmonic series diverges. The integral test also gives us a way to handle any series of the form 1 over n to the p. And we call those p series, and because we can compare them to like integrals, we know that these series will converge only when the like integrals converge, which is when p is greater than 1. So the integral test, very handy. We have a couple of other tests that deal with the relative growth rates of a series. If we can show that our series grows faster than a divergent series, we know our series will diverge. If we can show our series grows slower than a convergent series, then our series will converge. And we have two ways to do this. One is called the direct comparison test. If we can compare our terms of our series with the terms of another series, and we know how that other series behaves, we'll know how our series behaves. So if our terms are bigger than the terms of another series and that other series diverges, the sum of those terms diverges, then our series will diverge. And likewise, if our terms are smaller than the terms of a convergent series, then our series will converge. For example, if we wanted to explore whether the series 2 to the n over 3 to the n plus 1 converges or diverges, it might be a little difficult to do by simply looking at that series on its own, but we can show that term by term, our series 2 to the n over, or each term of our series is smaller than 2 to the n over 3 to the n, which is in fact a geometric series with a common ratio of 2/3. And since our series is smaller term by term than a convergent series, we can say our series converges. So our series of 2 to the n over 3 to the n plus 1 converges. We use the series that we know about from the integral test and geometric series as our comparers because we know how they behave pretty simply, and then we take more complicated series and make the comparison. In addition to the direct comparison, because sometimes numerically that direct comparison is a little difficult, we have what we call the limit comparison test. And the limit comparison test is similar. We compare the limit of the ratio between our terms and another series whose behavior we know. And if that ratio is some constant that's not 0, and we know if we get that constant ratio, then the two series behave the same way. So if the b sub n's, if that series converged, so would our series of a sub n's. And likewise, if the b sub n's diverged, so would our series of a sub n's. There are two other options for the value of this limit. It would be either the limit goes off to infinity, and that means that the series made up of the a n terms grows faster than the series made up of the b n terms. So if we also knew that the b n terms gave us a series that diverged, then we know that the a n's will give us a series that diverges. You grow faster than a divergent series, then you will diverge. And finally, if that limit went off to 0, meaning that the a n's grow more slowly than the b n's, and we also knew that the b n's converged, then we know that the a n's will also converge. Smaller than a convergent series will also converge. So we reviewed how to tell if a series of positive termed made up of positive terms converges or diverges. Why don't you go practice a few on your own?